In this video, I'm gonna introduce an algorithm on tree named SAG. Have you seen my blog on Codeforces catalog named SAG? This is the video version of it. Okay, so now everyone here, let's start with asking how many of you solved problem 600E? So people solved this problem, raise your hand. Okay, great. So for people who solved this problem, 741D, if you solved, raise your hand. Okay. So we have only about 4-5 participants solved first one, and no one solved this. Okay. So for people who solved this, you can continue with this. Have a good time. We are gonna solve the first problem. So the problem is very clear. It's very short. So it comes from the first educational runs on Codeforces. So I strongly recommend you to try first educational runs. They were very good trainings for knowledge and implementation and no creativity at all. So they were great if you are not intelligent that much. It's a good training for you to make sure you remember all algorithms you learned, like for training, participating virtually in them before regionals or before some important competitions is for sure recommended. The problem says we have a tree and every vertex has a color, and we call a color dominating in a subtree that no other color appears in this subtree more times than this color. So it's a clear definition. This color is dominating in this subtree. And it's possible that a subtree has a few different colors dominating. They are all equal and they are all maximum. So we need to find the sum of dominating colors for every vertex. Let me make it easier. Let's define the dominating color to be the smallest color, the color with the smallest index, actually. There is no other color in this vertex that dominates it. And also let me make the problem again easier to remove some unnecessary difficulty from it. In every vertex, there is only one dominating color. Find it. Lecture session is going to provide some problems. We will solve them step by step, and please don't shoot out the idea. If you know the idea, if you discover the idea, don't shoot out. Raise your hand. I will come near to you and you will explain your idea and I will verify if it's true or not. For this problem, let's make the problem even simpler. For each vertex, you don't need to find the dominating color. You need to find how many vertices are there with a specific color. Like there are queries of type V and C, and they ask how many vertices are there in subtree of V that their color is C. Clear? So now try to solve this problem. And C is different, okay? For different vertices, C is different. Otherwise, it was pretty easy. You need to somehow use the values calculated by your children. So when you are trying to find the color set for V, you need to somehow use color set from children of V. So let's say you have some map of integer to integer bag for each vertex. Bag of V is going to represent the number of times some color appeared in subtree of V. Like here is V, and bag VC is equal to the number of times C appeared in subtree of V. You need to calculate this bag somehow. So there is some naive way to do that. Like you want to calculate bag of V, you iterate over all of the bags of your children and add everything in them to your bag, and also you add the color of V itself to the bag, and that's it. But the time complexity is ruined, right? So can you tell me what is the time complexity here? In a squared look, we don't convert map to unordered map unless we get TLE and we want to try our chance. So sometimes it's worse than map, and there are some tricks to fix and reserve and other factors and something like that. So let's not go that way. The main point here is to calculate bag efficiently. So try your best, and a note here is you can solve the problem offline. So maybe you can answer the queries of the children and then the parent. And when you want to answer the parent query, you don't need the bag of children. Maybe you can ruin them. It doesn't have any problem. So if you solve the problem, raise your hand. I will come next to you, and I want to hear your solutions.
Other approach than this. I will think about other approach than this one.
Yeah, there is a very easy approach to solve this problem without all these difficulties, but we don't want to go that way. People who were able to solve this problem either before or now in the class with any time complexity, even n log squared is acceptable. Raise your hand, please. Okay, almost everyone. So I'm gonna tell you the solution for solving this problem in n log squared. So you have some bags of children and you want to fill your bag. So first idea is to start with your empty bag, empty pure each of your children's bag into your bag and go to the next, and finally put V into the bag too. But this will lead to n squared log. But you can start with something better. So if you start with empty bag, you have a lot of things to pour into your bag, right? What you can start with? Great. Largest bag. So if you pick largest bag, you already did a lot without doing anything. So you pick that big bag that already contains a lot of elements. For example, consider the case that vertex V has only one children. So that's done. And you just need to add this vertex. With having that big bag and adding all that vertices, tell me, what is going to be the time complexity if we use map 2? Yeah, n log squared. So when we pick the larger element and put all the smaller elements in it, we always find it's logarithmic. But why? Here, why?
Basically, it's like for every node, the time that we take is material log of non-largest. So it's like, in the worst case, that is n by 2, right?
The biggest one, not necessarily. It can have a lot of children, and the bigger one has something like n over 5 number of vertices in its bag. So that trick is not working here.
Let's say we have an element, and it's part of a group that's a size x. So the next time, if I put it in another group, it will be at least of size x. So now it's in a new group that's a size at least 2x, and it will grow on exponent. So next time it will be in a size of at least 4x and so on.
Yeah, that is now true. So let's use sack instead of bag, because the topic we are discussing about is sack. And to give you some historic data about this name, people always call this technique DSU on tree, or a smaller to larger technique on tree, and something like that. 10 years back, some teacher in summer camp in Iran called this topic sack, for sure not sack in Persian. So everyone in Iran started to name it sack. And a few years after that, I published the sack tutorial on Codeforces, and I named it sack. And after that, people started globally to use sack. So it's a meaningful name. Why? Because every vertex has a sack. my duplicate enters. So you get the sack from your largest children and pour other sacks into this sack and make it a bigger one that now it belongs to you, and you pass it to your parent. And it goes like that. So sack can be used in a lot of different problems. We'll solve some problems together. But first we need to focus how to implement that and learn how it can be efficiently implemented. So in this problem, we keep in our sack number of times every color appeared, and that's gonna be simply passed to the parent and all the calculation. Sometimes SAG can be much more harder. We will discuss that later. So there are a few different types of implementing SAG. You can find at least 4 on my blog on Codeforces, but I do think that recently I discovered something that maybe is better than all that 4 on my blog. I'm still unsure that this way can solve all of the problems, but I'm trying. So first, let's remove this map because it's producing another log factor. And if I remember correctly, I used unordered map instead of map during the contest. And you know, I was a child and it was my first time solving problem E during the contest, and it got failed because I used unordered map. So in this problem, 600E, so I'm old enough to participate in that contest. So, and I used unordered map because I thought that, you know, unordered map is constant factor, blah, 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 but they are all, you know, theoretically, unordered map is ON per query, theoretically. So yeah, sometimes theory happens in real, and it failed me, and it was a super pain. I was a school student that time. You know, I first solved problem E in a contest, and I was on air of happiness, and after the system testing, I got failed because that unordered map. So because of that, I never trust unordered map. I just try it randomly if I was unable to solve the problem using map, and I don't care about penalty, so let's submit again to see what happens. So it's my relation with unordered map currently. So now let's remove this map. To remove some unnecessary logarithm here, we will keep in our SAG vector of pairs, which means that from what color, how many times it appeared. So let me know, what is the problem now?
We reduce the factor of log n, so we get log n.
What?
We reduce the factor of log n.
No, I mean, you can't easily merge them. So do you have any idea how I can merge these two vectors?
Use mapping or coding compression.
It still doesn't work. Because it works if we have big coordinates and we want to map them to some small. But in this problem, it's not the case. For every vertex, if you want to map it, the mapping will be different for different vertices, so it will ring.
Maintaining a global array whose ith index gives the index of the ith color in the array that you're using.
So the thing is, how I'm gonna use this array for different vertices. You know, it's a global array, but if every vertex comes into it and rings it. So try to think a bit on how we can remove this logarithm factor. Maybe by using, the solution is to somehow using a global array, but let's see.
Someone using the idea of vector pair with elements and frequencies.
Okay.
That would
we are currently using it, but the problem is when you want to merge that, it will not work because we want to insert something in the middle and it will not work. Okay, let me describe the idea, but I was unable to find that easy way that I was thinking about. What we are gonna do is relatively simple. So there are some children. This one is big. We keep a global array CNT. We call DFS function for these elements and ask them to go solve for your subtree. I don't care. But make sure after you finish, CNT array is all 0. For big element, we do something else. We call the DFS function and ask it not to clear CNT array after its function is finished. So when this is done, CNT contains all elements in this subtree, right? Then what we can do?
if you have a vector pair,
No, we don't have vector at all.
we can run the DFS again and store the
Yeah, we do another DFS here, and we add all of the vertices easily to the CNT, and after that we have the SAG for these vertices. That's it. So there are two DFS. One DFS for calculating the answer. One DFS is for adding those things to the CNT. I was unable to find the way I was trying. So as you saw, if you were allowed to use map, it was much easier, the implementation, right? You just swap your map with your children, and then you iterated on other maps, and that's it. Or even easier, you could write a merge function for maps and check which one is greater and pure one to the other one, that's it. So it was very easy, even you didn't need to find the largest children. But yeah, here I was unable to do that. I was trying to do something with resettable arrays and something like that. So you can define an struct, like when you are done with using that, you can reset all its elements in time complexity of number of indexes that you use. That is pretty easy, right? So I was trying to do something like that, but it was not possible. For solving 600E, we are almost done because we have count of every single element, every single color. We just need to keep some helper variables, like what is the dominating number, so the maximum element in the array, and then we needed to keep some of them, and that's it. Thanks for watching. If you found this video useful, please like, subscribe, and ring that bell. By the way, YouTube thinks the video down here is just perfect for you. Give it a watch and let me know in the comments.